Hi everyone, and at the dimming of the light, this lecture begins, which will make more sense to you as this event goes on. Before I introduce our speaker this evening, Josue Fabiane, I just want to welcome you all to this Medieval Work in Progress seminar. This is a long-running seminar series sponsored by Sam Fogg. And also to alert you to the next Medieval Work in Progress seminar, which has just gone up online, so you might not have noticed it before. On the 22nd of April, George Bartlett will be speaking on the topic of a Byzantine icon of Christ Pantocrator. I probably garbled that, sorry, and its inscriptions. So do join us for George's lecture on the 22nd of April. So we're very pleased to welcome Josue this evening. Josue Fabiane is currently a postdoctoral assistant in medieval art at the Institute of Art History at the University of Vienna. His research examines the intersections of artisanal, scientific and religious knowledge, including the relationships between optics and architecture in Florence, as well as the fabrication, destruction and reuse of gilt metalwork altarpieces in Venice. His research has been supported by fellowships at the Bibliotheca Hertziana, the Max Planck Institute for Art History in Rome, the University of Hamburg, the Netherlands Inter-University Kunsthistorische Institute in Florence, and Bocconi University in Milan. Before all of that, Josue did his PhD at the Courtauld, supervised by Professor Joanna Cannon, exploring the making and meaning of luminous phenomena in late medieval Italian churches. And in fact, Joanna commented to me that Josue is the only student who might legitimately claim that he could only do his research on 1 or 2 sunny days of the year. Josue's current book project examines how solar time shaped the experience of religious paintings and sculptures across the Italian peninsula. And he's also currently co-editing a volume on Venetian metalwork altarpieces with Stefania Gerubini, which will be out later this year. Today, Josue will be talking to us about time, body and building, architecture and timekeeping in late medieval Italy.
Right, thank you so much, Jessica, for this lovely introduction. So I'm delighted to be part of this wonderful series and in the true spirit of the Work in Progress seminar. What you're going to hear today is very much a live issue. It grows out of my doctoral thesis, which I'm currently wrestling into a monograph on the visuality of time and the techniques of architectural lighting in medieval Italy. The church of San Miniato al Monte, as the name suggests, sits perched on a hilltop high above Florence. Founded in 1013 by Bishop Aldebrand, and soon adjoined by a Benedictine monastery. It was conceived as something of a spiritual citadel, an architectural outpost surveying the city below. The visitors ascend to the church, a punishing climb of hundreds of steps, is rewarded by a luminous facade, patterned in white and green marble and topped by a golden mosaic. Yet, stepping inside, the sense of soaring quiet is suddenly inverted, as the eye is drawn to the ground to meet one of the most remarkable floor pavements in medieval Tuscany. Extending almost the entire length of the nave, the pavement unfolds like a vast stone tapestry of opus sectile, crafted from local white, green, and occasionally red marbles. It is divided into quadrangular fields displaying a dense repertoire of imagery. Interlaced patterns reminiscent of textiles, real and fantastic beasts arranged in radiating patterns, and anchoring the composition, a striking wheel of the zodiac, with its 12 signs circling a radiant sun. This image of celestial and cosmic time is introduced by an inscription on the upper portion of the first ornamental panel, closest to the church's main portal. The text records that the floor was completed by 1207, and names its patron, a certain Joseph, described as Iudex et Metricus, judge and poet. It concludes with a brief prayer for his salvation, and I'm reading the inscription now. Before these doors, by concession of the heavenly God, Joseph, poet and judge, had this made. Therefore, I pray to Christ that he may always live in him. 1207. Remember the time. At first glance, the inscription performs the familiar task of commemorating patronage. Its closing phrase, retinut de tempore mente, asks the viewer looking down at the marble to remember the date of the work's completion. Yet time, as it turns out, manifests itself across this floor in another, highly visible way. Because of its elevated site, San Miniato is exceptionally well positioned to receive abundant sunlight throughout the year. At the peak of summer, when the midday sun climbs to its highest altitude, its rays plunge through the south clerestory windows at a dramatically steep angle. A sequence of bright, almost circular pools of light is cast downwards, rhythmically punctuating the central axis of the floor. What might initially appear an optical accident begins to look decidedly orchestrated when we examine exactly where these descending patches land. As the sequence forms, one pool drops precisely onto the sign of Cancer, a phenomenon first noted by Simone Bartolini about a decade ago. Note how this is the only sign in the zodiac wheel singled out by a circular frame. This emphasis is significant. In medieval astronomy, Cancer embodied the time of the summer solstice, a date, now falling on the 21st or 22nd of June, when the sun achieves its maximum visible height in the sky before beginning its slow descent toward winter. In concert with the building's upper fenestration, the ground-level zodiac panel functions as a monumental solar orologium. The sculpted imagery lies in wait for the descending light, rendering a specific celestial movement temporarily and cyclically visible at our feet. Did Florentine observers look down and register this phenomenon as meaningful? An authoritative source suggests that they did. In his Chronica, written by 1348, Giovanni Villani described a strikingly similar zodiac panel in the city's baptistry, noting, and we find in ancient records that the figure of the sun carved in the floor was made for astronomical purposes. And when the sun enters the sign of Cancer, at noon it casts light in that place through the opening above, where the little lantern is. Villani's remark is significant insofar as it shows that the perfectly timed illumination of a sculpted image of the zodiac may not have been unique to San Miniato. Yet the passage is also intriguing for what it leaves unsaid. Who devised such an arrangement, and by what architectural means was it achieved? What forms of celestial and artisanal expertise was required to align a descending sunbeam with a sculpted program on the ground? In what follows, I approach these questions by situating San Miniato within a broader medieval culture that made buildings function as monumental orologia. By this, I do not mean the installation of standalone clocks or sundials within the church fabric, though these were certainly important. Rather, I am referring to the subtle capacity of architecture itself to act as a temporal instrument, through the deliberate direction of natural light to interact with structural and decorative features. To understand this phenomenon, we must turn to a body of textual sources not usually central to art history, which nonetheless describe closely related ways of measuring time in architectural space. The first is the literature of surveying, the geometrical operations by which land, buildings, and horizons were aligned through calibrated sightlines. The second is the monastic tradition of the computus, the science of calendar making, and the coordination of sacred time with the rhythms of the sun. Though concerned with seemingly different domains, surveying and the computus share a key operation. They both rely on the precise positioning of the human body to align vision with celestial and architectural markers. Drawing on these two traditions, I will divide today's talk into two reciprocal modes of engaging with time and architecture. The first mode concerns sightlines, the outward projection of vision. Here, an observer deliberately positions their body on the ground to align the eye with a celestial point against the built horizon. Time is grasped by looking upward. The second mode concerns sun rays, the inverse operation. Rather than projecting the gaze outward, the observer tracks light as it descends from the heavens, entering the building and tracing its path across walls and pavements. Time in this case is registered as it falls into space. And I will start with the first part, sightlines. Despite appearances, the figure in this manuscript drawing is not enjoying a restorative nap. Lying flat on his back, he faces two upright objects: a rod positioned directly in front of him, and farther to the left, a crenellated tower rising some 4 stories high. Notice how his supine body is contained within a triangular field, which is itself nested inside a larger triangle. The body lies along the horizontal base. From the back of his head, a slanted line, the hypotenuse, passes precisely through his eye, connects with the tip of the rod, and finally strikes the summit of the tower. A vertical side of the tower forms the upright leg of the larger triangle, just as the rod forms the upright leg of the smaller one. Those of you versed in geometry will instantly recognize the principle of similar triangles here. By knowing the height of the rod and the horizontal distances on the ground, the tower's height can be deduced by proportional comparison. Our recumbent friend is therefore engaged in a task that would probably baffle most of us today, determining the exact height of a building using nothing more than a stick and the eye. Misurazione ad occhio, in the contemporary parlance of late medieval Italy, where this image originates. The drawing belongs to Giovanni Fontana's Trigono Ballistario, a treatise compiled in the first half of the 15th century during his travels between Venice and Udine. It is essentially a compendium of inventing measuring techniques. In one sense, the image is entirely conventional. It belongs to a long diagrammatic tradition in practical geometry and surveying, dating back to at least the 10th century, where determining the altitude of a distant object was a standard measuring exercise. What makes Fontana's image so arresting, however, is the vivid, rather uncompromising depiction of the measuring body. The figure is conspicuously stretched along a conceivably dirty ground. The figure, earlier depictions typically omitted the measurer altogether, while later Renaissance examples, such as those by Leon Battista Alberti, here on the right, neatly replace the human form with a disembodied theoretical eye. An earlier depiction in the so-called sketchbook of Villard de Loncourt does show a measurer at work, but he stands with a gentle sway, accommodating the slope of the terrain while holding his measuring triangle with dignified, courtly assurance. Yet in all these cases, the underlying geometric objective is identical. The eye must be brought as close as possible to the ground. Only then can the eye, the instrument, and the summit of the tower lock into a single unbroken line of sight. Shift the body even slightly, and the alignment is lost. The search for the correct vantage point thus constrains the entire body, forcing it into unusual or even uncomfortable postures. While performing a trigonometric operation of this kind was hardly a daily routine for the average medieval citizen, Fontana's drawing makes visible how the act of looking could be controlled by the demands of alignment. As if the desire to retrieve precise information about one's built surroundings imposed a physical discipline upon the observer. In recent years, architectural and art historians have increasingly emphasized how specific vantage points fundamentally structure the experience of sacred spaces. Simply put, it mattered who was looking, when they were looking, and precisely where they stood. Marvin Trachtenberg has famously characterized this visually orchestrated regime in the late medieval and early Renaissance city, particularly Florence, as a dominion of the eye. So here in a study of the Florentine baptistry, he claims that sightlines were deliberately manipulated to channel civic movement, and that the rebuilding of the basilica in front of the baptistry took the most ideal viewing distance and angle into careful consideration. This dominion of the eye intersects directly with the surveying operations we just examined, as well as with the measurement of celestial time. In a related set of techniques, also illustrated by Fontana, the measurements of a building's altitude depended on aligning the structure with the sun itself. Observers capitalized on discovered visual rules. At specific hours of the day, when the sun reaches an elevation of exactly 45 degrees, a tower's height corresponds neatly to the length of its cast shadow. The shaded ground itself transforms into a vast surface of measurement, and the building responds to the sun's movement like a giant sundial. My concern today builds upon the structuring force of sightlines, but I want to ask, how are these principles of bodily and architectural alignment exploited not just to view buildings or to measure their height, but to reckon time through them? And what happens to this visual discipline when we leave the public piazza and enter the more secluded spaces of the monastery? The foundation of reckoning time through the attentive recording of the shifts in natural illumination was, of course, the rule of St. Benedict. While the rule demanded a strict, seemingly universal schedule of daily prayer, called the horarium, harmonizing the monks' offices with the daily movements of the sun was a profoundly local challenge. The medieval hour was not a fixed, abstract unit. It expanded in summer and contracted in winter, its duration inextricably bound to latitude and seasonal drift. Even when water or mechanical clocks were available, they were prone to drift and required a constant calibration against the changing durations of the sun. Fulfilling the horarium therefore required a deep spatial as well as temporal awareness. Monks inhabiting the same spaces day after day observed how the same built surroundings responded to changing angles and seasonal rhythms. Local topography particularly dictated how and when the arrival of daylight was experienced. Take, for example, the monastery at Subiaco in the Lazio region of Italy. Clinging to the vertical rock face of Mount Taleo, this abbey was deeply shadowed by mountains that considerably delayed the arrival of the morning light and abbreviated the light of sunset. Here, the start of the monastic offices could not rely on abstract numerical hours. Rather, they were triggered by highly localized visual cues. According to Subiaco's 14th century customary, the bell for matins, for instance, was to be sounded incipiente luce or ingresso lucis, literally when light enters and when the light begins. Accurate timekeeping ultimately depended on watching the sun physically interact with the built and natural surroundings. The responsibility for identifying these precise transitions fell to the significator orarum. This timekeeper made time manifest to the community primarily through sound, summoning his brothers to the choir by tolling the bell. Yet his sonic authority relied entirely on a prior, rigorously visual form of perception. The core principle at play was architectural framing. Just as a surveyor uses a rod to intersect a line of sight, a monk could use the fixed masonry of a window jamb or a roofline to slice the vast, continuous dome of the sky into discrete, measurable units. By standing at a highly specific point, the observer waits for a celestial body, the sun or a star, to cross these architectural thresholds, turning heaven motion into a legible temporal event. Surviving timekeeping instructions scattered across customaries and liturgical texts from Benedictine and Cistercian foundations throughout medieval Europe reveal inventive variations of this technique for both diurnal and nocturnal timekeeping. At the Cistercian Abbey of Villers-en-Provence, we find this practice inscribed quite literally onto the building materials themselves. Fragments of slate slabs, unearthed at the site in the 19th century, preserve a set of instructions dated to around 1267 for regulating the abbey's water clock, or clepsydra. The text directs the reader to rotate the handle to correspond with letters on a complex clock piece. You can see a reconstruction in the corner of this clock face. Crucially, this calibration was dictated entirely by sighting the sun through the church's fenestration. The individual responsible for this task, likely the sacristan, was required to stand at a fixed locus, a site, probably in the choir, and carefully map the sun's transit. And I'm reading from the instruction now. While the sun is in the middle of the first window, put the horologium on the letter B. If the sun is between the second corner of the first window and the first corner of the second window, place the handle over C. If the sun is in the first corner of the second window, put it between C and D, etc. In other fragments of the text, the sun is described as appearing in medio muri, meaning the wall portion between the first and second windows. Through the system, the regular punctuation of the Cistercian windows acts as a massive architectural dial. The monk maps the sun's progression sequentially across predetermined voids, the windows, and solids, the walls, as well as the specific zones of each individual window, first corner, the middle, and the second corner. A similar principle governed the reckoning of the nocturnal hours, only this time from outside the building. An 11th century pocketbook belonging to an unknown Benedictine timekeeper in Alton, France, contains a section titled the Horologium Stellare Monasticum. It provides a list of stars to be observed in correspondence to the rooftop of the monastery dormitory. And the monastic foundation is not named in the source, so I've used this randomized Cistercian cloister as a placeholder. On the feast of the Lord's circumcision, when you see the bright star which is in the knee of our arctophylax over the space between the first and second windows of the dormitory, just above the rooftop, then go to light the lamps. On the feast of St. Agnes, do it when you observe the scales of Virgo raised high over the space between the 6th and 7th dormitory windows. This technique and the one from Villers similarly use visual clues provided by the alignment of celestial bodies and fenestration to kickstart an action of temporal signaling. Tolling the bell, lighting the lamps, turning the handle on the clock face. While monastic customers often omit the precise physical details of these observations, we know these temporal alignments were profoundly dependent on bodily position. Because the sun and stars shift their trajectories with the changing seasons, any intended correspondence between a star and a window could easily be disrupted. Since the architecture is immobile, the body must move. The Orologium Monasticum Stellare makes this disarmingly clear. On the Feast of St. Vincent, it instructs the viewer to quote-unquote step back a little from the usual spot towards the 7 juniper bush on the path to the well, so that you can see and count the windows. The monk thus needed to leave his ordinary designated site, locus designatus, continually adjusting his position through the seasons. At certain times of the year, stars would sink below the roofline, obscured by the building itself. By stepping back or moving to a different spot, the monk could regain a clear sightline. The building appeared smaller and more distant, and the previously hidden portion of sky came back into view, realigned with the windows. The principle of repositioning and reorientation would have come naturally to monks, cultivated through the mental habits imposed by disciplined routes and processional movements across the monastic complex. Later texts also allow us to measure the extent to which, even outside of monastic strictures, secular viewers train themselves in the same practice of architectural timekeeping. The approach resurfaces, for example, in the writing of Leon Battista Alberti. The champion theorist of vantage points, although normally understood in a strictly perspectival sense. In the Ludi Rerum Mathematicorum, he applies the logic of the positional gaze to celestial timekeeping. And I'm reading from the text. To know the hour in the night without any other instrument except sight only. Do like this. Note in the evening when the stars appear, and pay attention to which tree, or tower, or chimney, or some like thing it lines up with, as seen from this fixed spot of yours. And here I was hoping to capture a similar alignment with the chimney I sighted in front of my hotel, but I suppose light pollution in London is a real opponent to my monastic aspiration. But at least you see the small sickle of the moon. It is almost as if the world was, in essence, conceived as a vast field of potential alignments, provided that the eye, the object, and the celestial reference could be momentarily stabilized. Again, is Giovanni Fontana visualizes this sensibility with particular clarity. In one striking illustration from his surveying treatise, he presents a landscape punctuated by fixed and mobile targets. The familiar towers, the sun, a tree, and a 15th century favorite, a man hanging at the gallows. If I understand his reasoning correctly, he even proposes the problem of determining the height of a bird in flight, which is indeed very difficult to do. Yet, though possibly intended as theoretical extremes, these exercises reveal just how deeply ingrained the spatial worldview was, whereby elements of the natural and built environment were simply waiting to be caught in a sightline. For these pre-modern observers, the visual rays correcting airborne distances were far more tangible than our modern eye could fathom. Consider the Roman architect Vitruvius, who described a technique in the De Architectura for ensuring sufficient natural light in dense urban buildings. To test whether a neighboring building would block the sun from a window, he advised stretching a physical rope from the top of the obstructing wall, then directly through the window and down to the point of the interior where light was desired. If one could look up along the line and see sufficient open sky, the light would safely arrive. Here, the rope physically occupies the trajectory along which both light and vision must travel. The sightline is not abstract but materially tensioned in space. This provides a tangible counterpart to what medievalists often discuss rather abstractly as the extramission theory of vision. The medieval idea that the invisible rays physically departed the eye to grasp distant objects. In our earlier surveying diagrams, this principle was represented by simple inclines drawn from the eye to the tower. But Fontana shows the transformation of the ray into rope in another of his treatises, showing a variation of the Vitruvian technique. In the picture on the right, you can see the rope being propelled by an arrow from a domestic interior, straight through a circular window, to strike the midpoint of a tower outside. Even a geometric fiction could, in the hands of the surveyor, literally be stretched and materially verified. So far we have explored a mode of observation that runs upward, from the ground toward a distant celestial target. But directly sighting the solar orb in the sky, unless screened by latticework of glass, was an excellent way to damage one's eye. It was far more sensible to track the sun, as it were, by proxy. Luckily, sightlines had their exact mirrored counterparts in another phenomenon originating from the sun's interaction with architecture. The paths traced by sun rays. By channeling imperial light into long, directional beams, medieval windows certainly catered to a sense of divine presence. But on a strictly practical level, they made solar angle tangibly manifest in a way that was simply impossible outdoors. Here, the observer's task was to follow the ray of light itself as it descended from the heavens, passed through the window, and struck a specific target on the ground. Observers studied the secondary shapes it cast upon interior surfaces, the floor, a wall, or a column, much as we saw at San Miniato, and as Jan van Eyck would stupendously illustrate centuries later. This premodern habit of observing the sun by reflection, as it were, has deep Christian roots. In his commentary on the Gospel of John, Augustine noted, "How often is that from an illuminated object we know the sun to be risen, for we cannot watch it with our eyes. For even those who have feeble eyes are capable of seeing an illuminated and brightened wall, and in another illuminated body that sunrise is demonstrated to them." What Augustine framed as a theological metaphor for the indirect knowledge of God, medieval astronomers and even casual observers repurposed for its sheer temporal utility. We find this instrumental potential explicitly outlined in the Calendarium Reginae, composed around 1296 by William of St. Cloud. An expert astronomer at the University of Paris, William dedicated this text to Mary of Brabant, Queen of France. Consequently, it bypasses dense astronomical theory in favor of more practical and terrestrial applications. He explains that if a church is perfectly oriented towards east, a light beam falling from a southern window can be used to reckon the hour of noon. And I'm reading from the text. "It is appropriate that the church shall be built in that way, so that through it the hours will be known. And this in fact happens when the church is located along the line of the true east. When a solar ray entering through a certain window, located on the southern side, falls perpendicularly in the church, it will certainly be noon. And depending on how much that ray will be far from that spot, before or after, it will be possible to determine the other hours." So, while monks at Villers track the sun through the fenestration by anchoring their own bodies to a precise point in space, William's method inverts this logic. It relies entirely on illuminated surfaces within the church, waiting for the light to occupy a predetermined spot on the floor. but to measure those relative distances before or after noon reliably, that central spot on the ground had to be physically marked. It required a visual sign to stabilize the fleeting light, precisely the role played by the symbol of Cancer on the San Miniato pavement. For that practical instruction, we must turn to another William, writing for a more restricted audience of monks 2 centuries earlier. William of Hirsau, a formidable 11th century Benedictine abbot at St. Emmeram in Regensburg, Bavaria, provides instructions for making ephemeral tracings, marks likely made in paint, chalk, or charcoal that have long since vanished together with its medieval setting. And I must acknowledge here the work of Philip Notaft from Oxford, who is publishing several of these texts related to the computers and has made them admirably accessible to a broader public on like art historians. In his Astronomica, a textbook for the monastic school at St. Emmeram, he instructs the reader to find a room high enough to allow the sun to send long beams through its windows. The observers sought to, quote, find a spot on the northern wall or column or floor that is always hit by the sunbeam around noon. And this spot, at this spot, draw a straight line pointing a long way downwards. The reader is then invited to trace the daily incremental creep of that light patch along the trace meridian line, marking the beam's lower border with horizontal lines and calendrical labels. And I want to show you this procedure here against the resulting diagram containing the only surviving copy of the stacks shown on the right. While visually underwhelming on the page, you can clearly make out the calendar labels, the calends, nones, and ides, translating to specific dates in April, May, and June. So this is just to visualize the process of first tracing this meridian line on the floor, which is precisely oriented towards north and south. And then, over a period of a year or multiple years even, the monk maps the moving light patch, and when the light strikes the extreme position on the top of this line, this spot will be the correct date of the summer solstice in June, right, the solar extreme. So the symbol of Cancer at San Miniato marks this extreme point of the yearly path of light onto the floor. Other similar treatises, such as this anonymous astronomical text now in Vienna, also recently studied by Notaft, offer slightly more precise visualizations of these graduated markings, once visible inside the monasteries. And as has been rightly noted, these bear a striking resemblance to the monumental Cathedral Meridiane of the 16th century and beyond. Crucially, with this method, rather than craning their neck to look upward at a distant celestial elevation, the observer simply drops their gaze, following the sun's motion as it is projected onto the interior architecture. These luminous patches also function as the optical inverse of a sundial. Time is still registered at the boundary between light and shadow, but instead of tracking the dark edge of a shadow cast by a stick, the observer tracks the edges of the light itself. This principle was not confined to floors, as William of Hirsau admitted. It could scale vertical surfaces, climbing walls and pilasters, and even mark dates of highly localized, rather than strictly astronomical significance. At San Urbano in Apiro, a remote 12th century church in the Marche region, you will find a carved circular frame on an engaged pilaster next to the doorway in the counter facade. It sits perfectly positioned to catch a patch of light cast by a small oculus in the apse soon after sunrise. Once adjusted for the differing days between the medieval and the modern calendar, the day this illumination occurs corresponds to the feast of the patron saint, St. Urban, on the 19th of May. We now describe instances of buildings whose surfaces were deliberately marked or even strategically decorated to capture calendrical light. But what actual function did the spatial intervention serve for the communities that inhabited these churches? At stake here is the word of the computus, the mathematical and observational science of timekeeping, through which medieval scholars created the calendar, determined the shifting dates of movable feasts such as Easter, and harmonized the daily movements of the sun with the rhythmic celebration of the monastic hours. The summer solstice, the longest day of the year in mid-June, carried enormous weight in a city like Florence. Following close to the feast of its patron, St. John the Baptistry, on the 24th of June. The two events were believed to have once coincided. Similarly, the spring equinox was believed to fall on or close to the feast of the Annunciation, which, as it happens, falls exactly today. Easter itself was entirely dependent on such solar terms because its date was dictated by a notoriously convoluted rule. It must fall on the first Sunday after the first full moon after the spring equinox. And here the Church faced a rather embarrassing problem. The Julian calendar was slowly drifting. As early as the 4th century, the clergy noticed that the real astronomical solstices and equinoxes were slipping backwards against their prescribed liturgical dates. By the 12th century, for example, the actual summer solstice was no longer landing on the traditional 21st of June. The light was arriving a full week early, around the 14th. This slow but relentless drift became a source of profound institutional anxiety, not least because it was so publicly visible, especially in comparison with the impeccable Jewish and Islamic calendars. One did not need to be a university-trained computist to notice that the heavens were out of sync with the ecclesiastical calendar. The evidence was quite literally projected onto floors and walls. As Roger Bacon complained in his Opus Tertium of 1267, this temporal discrepancy could be certified by any layman. By the way, a sunbeam falls on a wall or other object, sometimes higher, sometimes lower. Even the rustici, the peasants and farmers, were acutely alert to this displacement, because their livelihoods depended on reading the precise rhythms of the sun. The 12th century author of the Computus Petri lamented that the winter solstice was no longer falling on Christmas Day, but on the feast of St. Lucy, as the peasants say and hear. For church authorities, this was a deeply uncomfortable reality. If an ordinary layperson standing at their own window could empirically prove that the official ecclesiastical computations were wrong, the remedy had to be urgent and it had to be observational. To reclaim temporal authority, it may have been desirable to create a precise solar orologia that monitored calendrical time with unassailable accuracy. Let us return then to our church on the hill. In the period during which San Miniato was built, a renewed wave of astronomical learning was taking root within monasteries. When the Chronicle Giovanni Villani noted that the Florentine baptistry zodiac was designed per astronomia, he was gesturing toward this exact culture of scholarly observation. At San Miniato, one must imagine viewers, monastic and lay alike, watching light travel up and down the floor, tracing the path that mirrors in reverse the celestial dances of the sun. To my knowledge, it stands as the only surviving instance of a medieval orologium still operating through architectural lighting. San Miniato sits squarely within this astronomical tradition, yet it also invites considerations of its artisanal factor. The visual phenomenon relies on several structural variables. The spatial orientation of the church, the height and pitch of the clerestory windows, the breadth and width of the floor, and the axial placement of the opus sectile pavement, itself composed of multiple spatially organized panels. Did the builders here conceive of fenestration and solar trajectories on the ground as a unified program from the start, when the church was started in the late 11th century? And if so, what manner of building expertise did that require? To grasp the feasibility of such architectural undertaking, we need only glance across the broader Mediterranean. Between the 10th and 15th centuries, the construction of buildings as solar instrument was not only possible but, in certain contexts, highly developed. Across regions from Al-Andalus to Cairo, Tabriz and Samarkand, astronomical knowledge was embedded in architecture, often relying on the visual ingress of light from attentively oriented openings, striking meridian lines on the floor. These were purpose-built institutions, financed by a princely patronage, and with the involvement of specialized astronomers. A synthesis of these textual sources for exactly this phenomenon was offered by Aydin Saile in this book on the left, who documented observatories and related structures, now almost entirely lost, across the Islamic world. Evidence of this technical culture also reached the Latin West. The 13th century Libro del Relogio del Palacio de las Horas, composed as a section of the famous Liber del Saber de Astronomia at the court of Alphonse X by the astronomer Isaac ibn Sid, describes the construction of a circular building whose windows are precisely oriented to admit sunlight at designated hours in striking points on the ground. Its construction relies on procedures familiar from surveying, the use of sighting instruments, the stretching of ropes from the ground to determine the exact height and inclination of window openings. One image here on the right is meant to provide a flattened view of the south wall with its 12 slit windows and a doorway with horseshoe design. And I think it's quite clearly Andalusian character of this architecture. Nor were such operations confined to purpose-built observatories. As the 15th century astronomer Jamshid al-Kashi recounts, an existing mosque in Samarkand was modified with a circular aperture in the mihrab to admit light exclusively at the moment of afternoon prayer. These examples are geographically distant, yet they demonstrate the spatial and technical knowledge required to coordinate solar angles and build forms was well within the reach of pre-modern builders. Which brings us back to Florence. At San Miniato al Monte, the main phase of construction is generally placed in the late 11th century, while the inscription on the pavements provides a terminus of 1207. How and at what moment was the coordination between solar time and floor decoration established? Broadly speaking, three possibilities present themselves. The first is that the idea was set very early, during the laying of the ground plan, which inherently required the shadow of a stick, called gnomon, to align the building with the solar course, a procedure documented by several medieval liturgists. A second possibility is that the opportunity was seized mid-construction, once the nave walls reached the height of the clerestory windows. Though this would have required intervention to dovetail precisely with the building's internal proportional system. The third, and perhaps most intriguing option, is the empirical one. With the windows newly installed, the rays of midsummer sunlight struck the unfinished floor along the central axis. An attentive observer noticed the recurrent phenomenon, marked the exact spot, and the pavement was subsequently laid to meet it. If this latter scenario is true, it means a single, transient pull of light dictated the layout of the entire decorative sequence. The zodiac panel established the generative point, and the rest of the marble tapestry was arranged in its wake. These possibilities all bring to the surface a much larger historiographical knot, one that architectural historians have also framed as the profound relation between building and time. As we know, medieval builders were not handed a tidy, comprehensive set of blueprints. Buildings grew diachronically, and construction sequenced through pragmatic decisions made on site over decades and often centuries. If these luminous moments were indeed anticipated, how are we to reconcile this with a process of construction that was, by its very nature, incremental? Indeed, how could an entire architectural program be organized around the expectation of a single future visual outcome? Regardless of the precise sequence of construction and decoration, what is virtually certain is the presence of an active, measuring body, standing within that nave. We must imagine an observer, be it a monk, a surveyor, or a specialized builder, testing the space in situ, sending their gaze upward from the pavement to the heavens, fully anticipating the moment when the sun would complete that same trajectory in reverse, descending through the window to land at their feet. Coming to my conclusion now. I hope this talk has shown how the horological use of buildings was enabled by a shared visual culture of sighting, tracking, and even contemplating the dances of the sun. Art history often defaults to a Bourdieu's anagogical view of light as spiritual aesthetic wonder. But the phenomena we encounter at San Miniato also point to a complementary, profoundly functional and empirical way of experiencing light. Time itself in the Middle Ages was notoriously difficult to pin down. As Augustine of Hippo famously asked, quid est tempus? What is time? If time resists definition, it also resists visualization. And yet in the later Middle Ages, painters in particular devised increasingly sophisticated ways to render it. This is especially evident in narrative scenes, where the articulation of a before and after becomes essential to meaning. And this is something I have learned on many occasions from Joanna Cannon, and I'm especially grateful that she is here today. I would therefore like to conclude by pushing my argument forward and ask whether our sightline-based way of reckoning time, the meeting of celestial bodies and buildings, may have shaped in any way its visual representation in painting. We find a brilliantly eloquent echo of this idea in two celebrated scenes from Pietro Lorenzetti's Passion Cycle in the lower Basilica of San Francesco in Assisi. These images were made for an audience of Franciscan friars, and were placed as part of Christological narratives directly above important doorways. Thresholds the friars used daily as they left the liturgy in the choir and returned to their occupations in the cloister, the chapter, and the refectory. In both the Last Supper and the Capture of Christ, a starry sky unfolds across the pictorial field. The moon shifts perceptibly from one scene to the next, functioning as an ingenious indicator that time has indeed passed. The analogy with horizon-based timekeeping becomes especially pointed in the Capture of Christ. Here, an exaggerated sickle moon descends behind a sharp, rocky outcrop, just as Christ is seized directly beneath it. The rock functions as a fixed horizon marker, registering the moon's descent with dramatic clarity. Just as the moon is bound by its regular cycles to vanish behind the stone, so too does Christ's passion unfold with an air of inevitability. The foreordained trajectories of the heavens become a somber reminder of his predestined suffering. Yet it is in the Last Supper that the principle of celestial alignment assumes a more explicitly architectural form. The detail is less immediately legible, in part because of the fresco's damaged condition. Yet conceptually it resonates even more closely with observational timekeeping. The moon appears in transit behind an open loggia, suspended within a square aperture of sky, framed by slender, originally gilded columns supporting a trabeation. Here, architecture segments the sky into measurable units, transforming the moon's trajectory into a sequence of foreseeable alignments. The moon hovers between the second and third columns, poised on the threshold of its next interval. We can almost anticipate its eventual passage towards the space between the third and fourth columns, much as in the textual traditions that describe nocturnal timekeeping. Sienese painters like Lorenzetti were particularly attuned to the visualization of temporal change. In this specific case, I suggest that when tasked with rendering sequential narrative and anticipation, both essential to these scenes, Lorenzetti turned to visual formulas they reflect an instinctive habit of seeing. He relied on a mental disposition to register temporal progression in structural and spatial terms. In this sense, these images invite us to see through the eyes of those medieval observers who were able to read time against the fixed boundaries of the built and natural environment. Ultimately, they allow us to inhabit a gaze long removed from our own, bringing us a vital step closer to experiencing a truly medieval way of seeing time. Thank you.